Okay, hi, hello, good afternoon. Welcome to section number 2. So if you haven't already, take a moment to scan the QR code here. And oh my gosh, it's personalized to the lecture, atomic orbitals, reaction. Wow, crazy how that happens, crazy. And I think today's fun question is, what's a hot take that you have? So, my favorite answer of the fun facts for section 1 was someone said that they had a former pet rat named Becky. I love that. I need to figure out, I need to go and remember who that is. I'm still, again, horrible with names. My 3 kind of reminders at the start of class today are 1, horrible with names. So when we raise hands question things, we're going to do, hi, my name is blank, my question's blank. And then also when y'all are doing some of the practice that I have for you today, I'm going to be starting to quiz myself and I'll be asking what's your name? So I'll be working on that. Second thing, a disclaimer I normally like to give is I can be a little sassy sometimes. And a little sassy does not always mix well with a stressful class like organic chemistry. So sometimes a sassy comment can come at a wrong moment, in which case I misread the situation. I'm very sorry. I do not mean it in a antagonistic way. I mean it in a way of I'd rather talk about molecules kind of upbeat rather than yeah, the nucleophile is going to donate its electrons into, we're trying to be a little bit more engaging. So apologies if there's ever a mismatch there, and feel free to call me out about it or talk about it. Third thing was, if you are a person who requested printed materials for the semester, and you have not gotten this orange book, then I will be getting it to you sometime during this section or after section. And I just have to cross off names on the list because we only have enough for the students who ordered them. And then if students still want some, we can maybe place another order. Any logistical questions before we jump into things? Groovy. So, game plan for today. We have 3 big sections. First big section's functional groups. Second big section is MO theory. And then lastly, we have acidity. So we're going to do 2 kind of hard transitions in the middle. And then one thing that I have borrowed from, sitcoms and TV shows of my youth, when we have a transition, I have transition music to just bridge the gap. Because, it's going to be a really hard pivot from we're talking about one thing, now we're in a very different place. So I will try those out. The audio has been a little bit weird, but you will see. So let's jump into functional groups. So functional groups are groups of atoms within a molecule that have distinct properties and react in a characteristic way. Functional groups are our way of tagging little parts of molecules to understand how it's probably going to react. So it's going to be a really foundational skill for you to be able to look at a molecule and get a lay of the land of what's going on. So the definitive list of functional groups that you need to know is this list right here. So I've tried to make it look colorful and pretty and everything. Logan was saying refer to the problem set, but this is going to be your kind of definitive one. The problem set I think has one more that is a less common one called a thioether. You don't need to worry about that. But I'm going to talk through a little bit of these just because we didn't do much of it in lecture. And then there's going to be some practice where we're going to ID the functional groups and these molecules. So, starting off with the hydrocarbon family. So these family functional groups only have carbon and hydrogen in them. And the first one is actually kind of not a functional group. It's the absence of a functional group. Alkane, A for absence, maybe. And here I've used this R abbreviation. R is just a shorthand for something else. Typically what we mean when we put an R is an alkyl group, just hydrocarbon, more hydrocarbon going off to the side. So, for example, this R group could be an ethyl, 2 carbons, or it could be a methyl, or it could be an isopropyl or whatever. We don't care, because no matter what it is, as long as it's carbon and hydrogen, it's still an alkane. Now, if we have a carbon-carbon double bond, suddenly our A becomes an E. We are an alkene. And then alkenes, you can either have hydrogens or you can have alkyl groups attached to it. That's what this R/H means. You can either have carbon things or hydrogens attached to it. Then if we have a triple carbon-carbon bond, it's called an alkyne. And the nice like little pattern here is like as you go from single, double, triple bond, you go to A, E, Y. It's in like alphabetical order. So that's at least how I first was memorizing it. And then if we have double bonds on every carbon in a ring, we call that an arene ring. A-R-E-N-E. You might have also heard it called an aromatic ring. That's also fine, but it's just a longer word to write. So I like arene. That's the hydrocarbon family. Up next, we have the heteroatoms, which I call the oxygen mafia, because it's oxygen and like all of its little family members. So our base functional group for oxygen is an alcohol. And then if instead of an oxygen we have a sulfur, we call it a thiol. Now, it still has this OL ending because it reacts really similarly to alcohols, because remember, oxygen and sulfur are in that same like column of the periodic table, column 6. Yeah.
What did you say about being the base? Alcohol was the base of.
Oh, like the most basic oxygen functional group. Sorry, and by that I don't mean like bases and acids. I mean like simple basic. Yeah. I should maybe say the most foundational oxygen functional group. So then, an alcohol has a carbon thing on one side and a hydrogen on the other side. But if we have carbon things on both sides, then we call it an ether. Now, if both sides of your ether are connected and form a little three-membered ring, that's Miss epoxide. And epoxides, for example, are very, very reactive. So they are like an explosion risk for epoxide reactions. So I don't think that y'all are doing any epoxide reactions in lab. In lecture, we're going to do some, but yeah, I know. Okay, so another variant of kind of ethery things is if it looks like we have two ethers, but they are both connected to the same carbon, then we call it an acetal. So if you were to look at this and you were to circle this and say this is an ether, we would have to mark that wrong. And it's because ethers react in a very particular way, and acetals react in a very different way. And this overall is an acetal, and it's going to react like acetals, not like ethers. And so that's why, even though they have this kind of component ether section of it, overall it's an acetal. Is that okay? Okay. And then let's say we want to become an acetal, but we're not fully committed. We have one of our little ether subgroups, but then we have an OH. We're halfway there. We're a hemiacetal. Hemi for half. Then, if we have a nitrogen, generally speaking, it's an amine. And this notation here means that we have three things, and they could be carbon things, or they could be hydrogens. So it could be like NH2, so two hydrogens, one alkyl group. It could be all carbon things. So that's also an amine. Then last one in here is alkyl halide. So this is if we have a halogen, we call it an alkyl halide. So that's the oxygen mafia. Last group are the carbonyl compounds. So let's start off with the carbonyl. That's what we call a CO double bond. But a carbonyl is not a functional group. It's not a specific functional group label. Specifically, a carbonyl is an umbrella term. And so if you write carbonyl on the functional group part of the test, we cannot give you a point. It has to be one of the specific flavors of carbonyl. So can we all say that a carbonyl is an umbrella term? A carbonyl is an umbrella term. Cool. So the most foundational, not basic, types of carbonyls are ketones and aldehydes. So if we have carbons on both sides, then it is a ketone. Welcome. If we have a hydrogen on one of the sides, then it's an aldehyde. And the little biology mnemonic that I remember from this is ketones can be in the middle of a big molecule because carbons on both sides. The aldehydes, because they have to have a hydrogen, aldehydes can't hide. They're always going to be on the end of the molecule. Then let's think about we're combining a carbonyl with an alcohol here, and we call that a carboxylic acid. Now, why does this react as a separate thing than just a carbonyl and an alcohol? Why do these react as one thing together? Any ideas? Yeah, the question is, this carboxylic acid, it has an alcohol in it, but why is this going to react differently than just an alcohol up here? Why is it its own separate functional group? Yeah. Say yes. And what's the answer to like 80% of the questions that we ask in this class? Resonance. So let's maybe look at this. Does she appear to be sp3 hybridized? Does she have a lone pair? And she's adjacent to a pi bond, so she's actually sp2. And she has resonance that looks like this. So we could have the OH here with a plus, O minus. So because there's resonance, the electrons on this react as one complete group rather than an alcohol and a carbonyl. Hence why we would call this a carboxylic acid. Then if we have a carbonyl and something that looks like an ether, then we call that an ester. So anytime like I'm waiting for like a coffee order or something, I hear like large latte for ester, I'm like, oh, carbonyl and ether. Yeah. Then if we have a carbonyl and amine, we're an amide. And if we have a carbonyl and a chlorine, we are an acid chloride. The one odd one out here is this nitrile, which is a CN triple bond. It's unclear why we are putting that in this family now, but when we get to lecture 5, we're going to learn the reactions of this group, and the nitrile does a lot of similar reactions to the other ones around here. Yeah. Yep.
What's the R divided by H?
This means either an R group or a hydrogen. So like this could be hydrogens on both sides, that's an aldehyde, and that's the molecule form aldehyde. Or it could be just like part of a carbon chain. Yeah.
Oh, I'm Aria.
Aria. Yeah.
Could you just just go over, it's like tangentially related, what are the 3 things to look for that like
Neighbor rule.
in case it's an sp2 or not sp2?
So neighbor rule, it appears to be sp3 hybridized. It has a lone pair, and it's adjacent to a pi bond or an empty p orbital.
Not connected to, but adjacent.
Adjacent to, yeah. And so, in fact, this, and this are all neighbor rule like sp2 hybridized. Yeah. And actually this one too. Yeah. But I'm going to keep on moving a little bit. So one thing that was not explicitly touched on in lecture, but does come up in lectures 3 and 5, and so I want to just introduce the idea, is the idea of compound functional groups. So if we have 2 functional groups right next to each other that are connected, especially if they're connected via resonance, then they become a new compound functional group. And we've already seen that with like an alcohol and a carbonyl or carboxylic acid. So here, if we have an alkene and a ketone, it becomes an enone. And enones have resonance here, so it reacts as one group. And you're going to learn reactions with enones in lecture 3, so that's why I brought it up. And then here, if you have an alkene and an alcohol, this is an enol functional group, because, yet again, she has resonance. So, if we had another carbon between them, though, what's the hybridization of this carbon? sp3, and she doesn't have a lone pair, so she can't do neighbor rule stuff, right? So can we have any resonance between this and this? No, because what type of orbitals do we need for resonance? P orbitals, exactly, and this has no p orbitals. So this would just be a ketone and an alkene. They would be separate. But we are not going to test you on these. This is the testable list for the exam question. So we're going to take a few minutes, and I'm going to have you look at these 2 molecules and try to circle and name as many functional groups as you can find. And then, so sorry if you're a paper user, I will ask you to draw the molecule real quick. Yeah, these are just ones that I made up.
What's the Abby and Monica for that?
Does anyone want to help out with that? Does anyone know methyl? Yeah, so it's CH3. Mm-hmm. You love this stuff, right? Okay. I did see it on your, there were 3 names. I took a guess, but yeah. Okay. Are you Nate? Okay. What's your name? One more time. Simran. Simran. What's your name? Evie. Aside. Asias. Work. So Nate, Evie, Simran, Asias. Jerry. Are you Dylan in the back? No, what's your name? Sue. Work. Ahmad. Ahmed. Okay. Sue Ahmed. Can you give me the first letter? N. Don't tell me. N. Not me being like Nancy. No. But.
It's short.
Nina?
It ends with an though. Like with the sound with the letter A.
Okay, tell me. Nora. Okay. Nora. Lavidia. Okay. Lavidia. Ahmed. Nina. Sue. Nate. First letter for her. S. So sorry. You told me 2 minutes ago. I'm gonna look at lists and see if I can get it from Simran. You're Simran. First letter. Evie. First letter. One more time.
Give the pronunciation of it.
Asias.
Yeah, it's like Elias, but with an S instead
Work.
of an L.
Work. Say it one more time.
Asias.
Asias. Jerry.
Yeah.
Alyssa. We're working. Mhm.
Do the two R groups have to be the same?
No. Any 2 art groups. Good question.
Oh, you go back to the page.
I'm putting up the answers. Sorry. Okay, I know you probably did not have enough time to find all of them, but how did you do on the ones that you did have time to do? And if there were any that you gave a different name, can you ask me about it and we'll talk? Smear? Smear? No. Smear? No.
Like the season.
Summer? Do you prefer summer or smear?
I go by summer here.
Okay, cool. Word.
It's not like you pronounce it wrong. So it's summer.
Summer.
Summer. It's
Summer. Summer. Work. Okay. Any questions about the functional groups here? Yeah.
What does the on the second one, like the one to the right, and then the yellow group all the way to the left, the oxygen double bond with it?
This one?
No, to the one on the other
Say
side.
acid.
No, the other side.
You said the left molecule.
No, the right. You're on the right.
The left, yellow on the right molecule. Like the
This?
Yeah, that
So
one.
sorry. That says acid chloride. Yeah, and it's because we have a carbonyl next to it. So a carbonyl next to chlorine is our acid chloride up here.
Oh, I see.
Yeah.
Okay. Thank you. Sorry about that.
Wow, yeah, no, sorry.
No.
Yeah. Mm-hmm. it needs to be attached to three things, but those things could be carbons or they could be hydrogen. And they don't have to be the same. Yeah. Yeah.
But the carboxylic acid at the bottom, it has that like third branch. Why is it like not? Like it's so Y shaped.
Like you circled this whole thing?
Yeah.
You can. We're not going to be picky about the circlings. Yeah. Yeah. Mm-hmm.
So for the N in the middle on the right hand,
This?
yeah, that
Yeah.
one.
Why is it not an amine?
Like we can't say that it's gonna be
No, because it's right next to the carbonyl. And so she's going to have resonance here that's going to react as one group.
Oh, okay.
Yeah. Gary.
Like, I'm kind of confused with the drawing of the epoxide. Like,
So an epoxide just looks like a little triangle.
okay.
So like that's an epoxide triangle with an oxygen.
So like all the carbons like have to bond with the oxygen in a triangle.
Yeah, the two carbons on two adjacent carbons need to be bonded to each other and to the same oxygen.
Okay.
Yeah. So, with that, I'm going to go on to one other topic that's closely related here, but you have not technically seen it yet. It is one that really fits with this skill of IDing parts of molecules and giving them names, which is why I'm including it here. And you're going to learn about it in, I think, lectures 3 and 5. It comes back in different pieces, but I thought I'd just preview it here. It'll take like 2 minutes. So not all carbons are equal here, and we classify carbons based on how many other carbons it's bonded to. So like this carbon up top is connected to one other carbon, so we would say it's a primary carbon, and we could indicate it with a 1 and a little degree symbol. This carbon's connected to 2 carbons, so it's secondary. 3, so it's tertiary here. 4, so it's quaternary here. And I should write that as 4 prime. So if I were to draw this, what type of carbon is this? Secondary. What about this? And then if I add another bond to it, it's great. So now alcohols and alkyl halides we can also classify based on that type of carbon it's attached to. So here this alcohol is attached to a carbon right here that's attached to one other carbon. That's a primary carbon. So we'd call this a primary alcohol. Then here we'd call this a secondary alcohol because it's attached to a secondary carbon, tertiary, so on. Same with alkyl halides. So let's look at the alcohol that we had over here. Is this a primary, secondary, or tertiary alcohol? Secondary. Beautiful. Now I'm going to ask you a tricky question. This alkyl halide, is it attached to a primary, secondary, or tertiary carbon? How many carbons is it attached to? One carbon, so it's primary carbon, so it's a primary alkyl halide. Cool. The one thing that's a little bit weird is alcohols and alkyl halides, it's about the carbons classification. It takes on that. But amines is a little different. Amines, it's the number of carbons attached to the nitrogen. So if the nitrogen has 1 carbon attached to it, it's a primary amine, whether or not this is a primary carbon. So it could be like this, a secondary carbon, we'd still call this a primary amine. Then here, secondary amines have 2 carbons, tertiary amines have 3 carbons. So this amine right here, is it primary, secondary, or tertiary? Secondary, it's attached to 2 carbons. And then we have one more amine right here. Oh, yeah, let's do this one first. So this one, is it primary, secondary, or tertiary? Primary, because it's about the number of carbons attached to it. And lastly, let's do this one. Secondary. Cool. Again, it's a really simple thing, but we want you to have language to talk about molecules because there are going to be some reactions that like only happen with primary and secondary alcohols, but not tertiary alcohols. Yeah.
I just had a question for the practice one that we just did.
Mm-hmm.
On the second drawing, in the second skeletal structure, the amine that we drew that we also labeled like as secondary, why is it an amine? Because here it says that it's NH3, like in the upper part.
So it's an amine is a nitrogen attached to 3 things. Those 3 things could be hydrogens or carbons or some mix of hydrogens and carbons.
Okay.
Yeah. Yeah, totally. Cool. So why do we do all this? Why does it matter? So let's say I am in ye olden days teaching organic chemistry, and I hand you a list of 100 reactions to memorize. I'm going to say memorize all these, whatever. You're just studying individual separate reactions without functional groups. Whereas when we have functional groups, what functional group do we have here? Carboxylic acid, and then here again, and then here again. So this is carboxylic acid. Then what functional group do we have in this right molecule? Alcohol. And what type of alcohol do we have for the first one? Primary, then, and then another primary. And then what functional group did we create in the product? An ester. So instead of learning a list of like 100 different reactions, because the things that are changing here are these R groups, right? They're just like alkyl chains, and these chains do appear in the product, right? We definitely see them there. They definitely have an influence. But in terms of functional groups, all 100 of those list of reactions could be summarized down to this one reaction, which is that carboxylic acids and alcohols make esters if you do it under acid. And so using this language of functional groups is going to be really helpful, so we don't have to learn 100 reactions. We can learn one. But then we're going to do that for like a bunch of reactions. I think you're going to learn 90 reactions like this over the course of the summer. So buckle up. Okay, that was functional groups. We're going to do our first hard pivot of the day. So let me see if the transition music will work, and if not, we'll see. So let's talk about MO theory. So MO theory takes us from Gin Chem atomic level to actually how our whole molecule is reacting, which is going to be important. So I'm going to start off with two key ideas. First key idea, the number of atomic orbitals for a molecule equals the number of molecular orbitals for a molecule. So if we can calculate our number of atomic orbitals, we know how many molecular orbitals we should have. Our rule is that if we are a hydrogen, then they have one atomic orbital associated with it, just an S. And then assume all other atoms have 4 atomic orbitals associated with them, an S and 3 Ps. So in C3H7O, well, we have 7 hydrogens, so those 7 are contributing 1 orbital. And then we have 3 carbons, 1 oxygen, so we have 4 other atoms, and each of those 4 other atoms are contributing 4 orbitals. So we're going to do 7 plus 16, which is 23 atomic orbitals. So how many molecular orbitals should it have? 23, because the number of atomic orbitals equals the number of molecular orbitals. Okay, in your head, try out C6H6. Do not say it out loud. Okay. Got a question? Okay. So, we're thinking, we have an answer, and then we're going to do on the count of 3, 1, 2, 3, and then say the answer, okay? We're all going to say it together. 1, 2, 3. 30. 30. Okay. So we had 6 times 1 plus 6 times 4. So 24 plus 6. 30 atomic orbitals. 30 molecular orbitals. Work. So that's first key idea. Second key idea is that for each bonding molecular orbital that we have, there exists an anti-bonding molecular orbital. So the way I like to think about this comes from physics, where when you combine 2 waves, you can combine them in special ways where something happens that's a little unexpected. So if you combine 2 waves in phase where all the high and low points are matching up like this, then they combine, they say constructively, and the amplitude gets bigger. And so you have this kind of bigger effect that comes out of combining them. Whereas if you combine them where the high points of one are with the low points of another, they cancel out, and that's called destructive interference. So that's kind of like the difference between a bonding interaction and an anti-bonding interaction. And remember, we know electrons are partially particle-like, partially wave-like. So this idea is important to keep in mind, especially because our intuition, we only see bonds written on the paper. So oftentimes it's easy to forget about anti-bonding orbitals. So let's talk a little bit about drawing these orbitals. You did some drawing in lecture. And And like for a bonding orbital, we know that like it's going to be in phase here, where the shaded parts are going to be together and the unshaded parts are going to be together. If we were doing an antibonding orbital, they would be out of phase, and so it would create an additional node here. But these are for symmetric bonds, where the electronegativities are the same. Let's talk about for when the electronegativities are different here. So, on bonding molecular orbitals, we're going to put larger lobes on the more electronegative atom. So, for a pi bond, CC, it's kind of like little loaves. And then for CO, which one's more electronegative? Oxygen. So, we're going to put kind of a larger lobe here. And we'll shade one of them. So that's our pi bond for CO, where it's a little lopsided. And then, for antibonding orbitals, it does the opposite. So we're going to have larger lobes on the less electronegative atom. So now we're going to have large lobes on carbon. So it's going to be this idea, but now we're going to make these lobes bigger and these lobes smaller. So let's say we were a molecule that was trying to donate electrons into the pi star CO. We wanted to put electrons into this orbital somehow. Should we attack the carbon side or should we attack the oxygen side if we're trying to put electrons in this orbital? Why? Who? You said oxygen. Why do you think oxygen?
I originally said oxygen because I was thinking like if you're trying to put new electrons in the orbital, oxygen 1 is more electronegative, and like we've already established that it's orbital, like so that's kind of there. So I was
Well,
thinking,
think about it this way. Oxygen already has a lot of electrons around it. So it has
oh, wait,
a
I'm
larger
looking at a
lobe.
different- Oh, I'm looking at a different
Work. So here, if we are trying to put electrons in our anti-bonding orbital, it's just simply bigger on the carbon. So there's like a bigger target to hit on the carbon side than the oxygen side. And then also think about bond polarity. So partial positive, partial negative. Carbon's going to be partial what? Partial positive. And oxygen's going to be partial negative. And so if you're coming in with electrons, you're going to go towards that positive charge. So for both those reasons, if we had a lone pair donor that was trying to put electrons into a pi star CO, it would attack the carbon. But the big idea that I want y'all to know and walk away from very confidently about is that when we put electrons in antibonds, the bond breaks. Because right now this carbon has 4 bonds and it can't have 5 bonds. This ain't Texas. So we need to break one of the bonds. And we break the bond that we put electrons into the antibonding orbital of. So we break that pi bond. So we're going to do some Pavlovian conditioning where we are going to say this statement 4 times. And we're going to start off quiet at kind of a whisper, okay? Electrons in, antibonds make the bond break. Okay, now we're at like a conversational level. Electrons in, antibonds make the bond break. Cool. Now, we're trying to get someone's attention from across the room, but it's not a large room. So, electrons and antibonds make the bond break. Now we're in the lecture hall. We're trying to contact someone across the room. Electrons and antibonds make the bonds break. Thank you. Thank you. And she's going to come back. She's going to come back later today when we do curved arrows. We're going to put electrons in an antibond. And I'm going to say, and what does it do? Thank you. Thank you. Thank you. You're all the like dogs salivating. No. But Pavlovian conditioning I found works quite well. Last thing on here, relative energies. So I like to think about all of our MO diagram as having energy buckets, which contain our different types of molecular orbitals. So our lowest energy bucket is sigma, then pi, then non-bonding or atomic orbitals, then pi star, and then sigma star. And the star is what tells us it's anti-bonding. So these, you have to memorize that order. That is just what it is. But then within the bucket, if you have multiple like sigma bonds, then you use your low energy trifecta here to determine what's the lowest in energy within the bucket. So if you had like CO, C and O are more electronegative than C and C together, so it's lower in energy. And it's not about difference in electronegativities, it's about overall electronegativity. So if I had a sigma NO, would I put it at position 1, 2, 3, or 4 relative? Like, where would I put a sigma NO in terms of energy level? The lowest, at 1 here. So we would have sigma NO. Because nitrogen is more electronegative than carbon, and so more electronegativity, so lower in energy. Now, this is where students make the most common mistake on MO diagrams. They think, okay, let's imagine this sigma CO is our lowest energy one. Well, then the sigma star CO should be our highest energy one. No. No. So the buckets, these are symmetric. The buckets are, but within the buckets, it's still the lower energy trifecta. So it's almost like we copy and pasted this directly up here and added a little star. So we still have the lowest energy sigma star is going to be our sigma star CO because it's the most electronegative. So that's the one thing that I see students like miss points, easy points on for exams. So let's do a practice. And for some of the practices, I like to make the last page of section a practice handout that just like puts all the practice in one. Normally, I like doing mostly questions from the problem set, but I wanted to do a full MO diagram with y'all just from start to finish to kind of show you all of the steps. I've also like listed it out very explicitly because also this is a skill that you want to get fast at. You are going to have a page of the exam that will be full MO diagram and then predicting how the molecule reacts. And we're going to do essentially all parts of that today so you get to see it. So, yeah.
Is it multiple MOs or just one?
We're just going to do one on the exam. Yes.
Multiple?
No, on the exam we're going to do one.
Oh.
Yeah. But then you're going to predict how that reacts with another molecule that we throw in there. So, let's do it for formaldehyde. This isn't in the problem set. This is just one that I got that is like a small molecule. So first off, we start drawing the Lewis structure. So we have CH2O. We know carbon's going to be our central atom. We make our single bonds. Let's calculate our number of valence electrons. So how many valence electrons does carbon have?
4.
And then oxygen? And then we have 2 hydrogens. So we have 12 valence electrons. So I have 2, 4, 6 already there. 8, 10, 12. But to complete octets, let's make a double bond. So we have our Lewis structure. We have our valence electron. Yeah. Anyway, then we are going to calculate our number of atomic orbitals. So we have 2 hydrogens, each contributing 1 atomic orbital. And then we have 2 other elements that are each contributing 4 atomic orbitals. So in total, we have 10 atomic orbitals. So how many molecular orbitals do we have? 10 molecular orbitals.
Wait, what about they have like this bonding orbital?
So non-bonding orbitals are molecular orbitals. And it goes back to the key idea, our number of molecular orbitals is equal to our number of atomic orbitals.
Oh, right, yeah.
So then our next step is list out all of the molecular orbitals. So my strategy is I start with the bonds because I can see them. 2 sigma CHs, 1 sigma CO, 1 pi CO, and then second key idea, if we have bonding orbitals, we have antibonding ones. So 2 sigma star CH, 1 sigma star CO, and 1 pi star CO. Okay, if I count these up, I only have 8 so far, so what are the last 2? Yes, the lone pairs and the oxygen, which we do as a lower N for non-bonding, and then they're on an oxygen. So I really like explicitly doing this step every time with the atomic orbitals because it lets me know if I've forgotten one. The most like not devastating, like it's not the end of the world, but like it's really frustrating. Like let's say there was like a chlorine or 2 chlorines and someone forgot the lone pairs. That's 1, 2, 3, 4, 5, 6 molecular orbitals that you've forgotten. That's like minus 3 points on the test, which is rough. So now that we have all of our MOs listed out, we list them in our energetic order. And we start with the buckets, and then if we have things in the same bucket, then we use our low energy trifecta. So what's the lowest energy bucket type of molecular orbital? Sigma. Okay, sigma CH, sigma CO, which one's lower in energy? CO, sigma CO. Then we have our sigma CHs. Then next lowest energy is pi, so we only have the pi CO. Then we have non-bonding, so we have lone pair on the oxygen. Then what's after non-bonding?
The pi star.
Pi star. Okay. So we have the pi star CO. And then up top we have sigma, but between our two, or sorry, up top we have sigma star. Between our two sigma stars, which one's lower in energy? CO. So literally what I'm going to do, because I'm on a tablet, is I'm going to copy and paste. And then I'm going to add a little star.
I have a question.
Yeah.
How do you know like how many like electron lines to be on the other
Like if there are two of them, then two. If there's one of them, then one. No, you're fine.
So if there was like 3, you do 3.
Yeah. Yeah. And if there were 7, you do 7. So then last step is you populate your diagram with the valence electrons. So we said that we have 12 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we are done. And it should be so that all of your bonds and any lone pairs are filled, and then your antibonds are unfilled. So we did that pretty quickly. Like I don't think that took more than like 6 minutes, but it takes some practice to build up the speed with that. So what I'd like y'all to do now, and I'll answer questions once I get y'all started on it, is I'd like you to look at page 29 of the problem set and this molecule hydroxylamine. This molecule actually used to hang in the science center. They had like a big model of it, and it looked very like cool and dynamic, but I think that they took it down maybe with the construction. But you're going to do the exact same process that we just did. So start off with the Lewis structure, valence electrons, atomic orbitals, list out the molecular orbitals, rank them, populate the valence electrons. And to be so honest, I'm going to give you like 4 minutes. Try to get through as much as you can. I believe in you. And I'm going to list this like this so you can kind of see the process. Cool. So you had a question?
So, for molecular orbitals,
Mhm.
will we need to draw the atomic orbitals on the side screens in, or will we just be drawing the molecular orbitals?
Just the molecular orbitals. Good question. Yeah, the atomic orbitals on the side is more of a gen chemie skill with MO theory. But yeah, this level is all we need. Yeah.
The more electronegative element is already also right?
For ranking the molecular orbitals, yeah.
Okay.
You're a lesson. Jerry. Asaya? Asayas. Work. Sai. Evie. First letter. Simran. See, once I like look at all the S names, I'm like, yes. But yeah. Okay, Nate. Tsu. And is it Tsu or Tsuchen? Tsu. Work. Ahmed. First letter.
No, the first letter. You gave me 3 names with the first letter.
One more time.
N.
Nina. No. Mm,
It's okay.
Nira? No.
You're close. This is what Conrad.
Nima?
You're missing a letter.
Nora. Oh, okay. Work. Then Summer, and then wait, L. Yeah.
Wait, it's a complicated name. It's not gonna roll off the tongue.
I was thinking like Lydia, but that's
really close, Lavinia. Yeah.
Lavinia.
Yeah.
Work. The lower energy, yes. And remind me your name one more time.
Rose.
Rose. Okay. And you're Fabian, right?
Yeah.
Work. Can you give me your first letter? How many syllables?
I guess how many syllables are
Just tell me.
Micah.
Micah. Work. Is that also like the mineral?
Well, it's not spelled the same, but yes. It's
Okay.
like, it sounds.
Work.
There's just an H in there.
Gotcha. Who are you? Gia. I should know that. We've talked literally every day. Gia, Micah, Rose, Fabian, Aria, Work. Yes. Summer. Nora. Okay. Lavinia. Yep.
If I the number of valence electrons, is this right? This is what I'm asking. Is the number of valence electrons the number of pairs that we draw in this?
Mm-hmm.
And the number of molecular orbitals is the number of dashes?
Yeah. Yeah.
And like also, is it always that the like electrons should fill all of them except the anti ones?
Yeah. Mm-hmm.
And the number of arrows that you go
Wait, are we doing both the examples on page 21?
No, just A. So, take a moment and check.
Or should we always draw the arrow on the side of with energy?
If it's not given, I would, because we're ranking energies. I'm gonna copy and paste this over here. So, 1 second. So, any questions on her? Yeah.
Sorry. Why is sigma NH high energy than sigma
OH? Because oxygen's more electronegative than nitrogen. Yeah. So generally what I found for most students is creating an MO diagram is not something that's conceptually hard. You have all the skills to do it, but it's kind of like spinning a plate and then saying the alphabet backwards. You're doing a lot of things and you're combining a lot of skills and we're asking you to do it quickly. So that's the thing that makes the MO diagram a little bit more challenging. But with that, I'm going to plow ahead and do the other half of MO theory for today, which is frontier molecular orbitals. So, frontier molecular orbitals are the molecular orbitals that most commonly react in a reaction. They are on the frontier of reactivity for a molecule. And for that, it's going to be your highest occupied molecular orbital and your lowest unoccupied molecular orbital. So this class is going to make you really good at spotting HOMOs and LUMOs. So why do we care about them? Because we don't want to be doing full MO diagrams for every molecule that we want to figure out how it reacts, right? We want to be able to see a molecule and just kind of be like, that's probably the HOMO, or that's probably the LUMO. So we need to get a short list of what are some good donors and what are some good acceptors. And for good donors, we need to think about the good donors are close to being the HOMO, right? They're going to be the highest occupied. So first they need to have electrons, and then they need to be higher in energy. So the best example of a HOMO or a good donor would be a lone pair. The one exception is lone pair and halides are not great. And it's because fluorine is super electronegative. It's holding its electrons really close, so it doesn't want to donate them as a lone pair. And then chlorine and the bigger halogens, their electrons are so far out that it's not condensed enough to be a great donor. So lone pairs are generally the best donors, and then after that, alkenes, carbon-carbon double bonds, just because you have 4 electrons worth of electron density in the same space, so it's a good donor. It's also going to be the next highest bucket after the lone pairs. Then our shortcut for good acceptors are 1, empty p orbitals, because that's going to be as low as an unoccupied orbital can be in the atomic orbitals camp. Then we have pi star orbitals, with the one exception of pi star CC. And that actually has to do a little bit with the shape over here. Like pi star CC, you don't have a bigger target, whereas like pi star CO or something like that, you do. And so pi star CC we don't say is a great acceptor orbital. And then the last good acceptor is a sigma star of some variety. Then this is talking about specific orbitals. This is talking about the way that orbitals can interact, but if we want terms to describe a whole molecule, we say in a reaction, the molecule that donates electrons is the nucleophile, and the molecule that accepts electrons is the electrophile. And then this is the way that I learned it, that a special type of nucleophile is a base. A special type of electrophile is an acid. And I think Logan teaches it slightly differently. I think for purposes of our class, you need to think about we're either in acid-base land or we're in nucleophile-electrophile land. But I like to think about this as bases are electron donors. So that's kind of our Lewis base definition here. And acids are electron acceptors. And we'll be able to see that more clearly when we have an example that we're walking through. You probably have the Bronsted-Lowry definitions more ingrained, which is acid. Bronsted-Lowry is a acid donor, or a H plus donor, and a base is an H plus acceptor. We're all saying the same thing, it's just what do we pay attention to, the hydrogens or the electrons. So I made a nice like little diagram. In that, in a reaction, the electrons are going to flow from the HOMO, which is the donor orbital that's on the nucleophile, which could be a base in a specific type of reaction. And it's going to flow from that HOMO to the LUMO, which is the acceptor orbital, on the electrophile, which could be an acid in that specific context of acid-base reactions. So let's see this in action on actual like questions here. So the first question that we are going to ask, and this is Skill Builders on page 38, is are we in acid-base land or are we in nucleophile-electrophile land? And the way that we ask that is we ask, is the only thing that transferred between the two molecules a hydrogen? If so, it's acid-base. So what about this one? Is it acid-base or nucleophile-electrophile? Yeah, I'll repeat it. I think I gave too long of an introduction. So we are trying to determine whether we are in acid-base land or nucleophile-electrophile land for our labels here. And the criterion for being an acid-base land is only a hydrogen is transferred between the two atoms. So does that look like the case here? Yeah, this hydrogen got transferred over to the other one. So we are in acid-base land. So we need to know which ones are acid, which ones are base. Well, you've probably seen one of these molecules before, so we know that this one on the right, H3O+, is our good acid. The other way to think about it is it's the electron acceptor, our Lewis acid here, because it wants electrons, it has a positive charge. Whereas over here, this nitrogen is the base, because it's the electron donor. Okay, so now let's think about on these molecules, what are the actual good donor and acceptor orbitals? So let's start off with the base. What's a good donor orbital on the base? Yeah, lone pair on the nitrogen. We also have lone pairs on sulfur, but the nitrogen is the one with the negative charge, so that one's probably going to be a better donor. So we have the lone pair on the nitrogen, and then what is our good acceptor, I guess, of the acid? And to think about this, let's think. Okay. Well, we know that this lone pair is going to go and grab the hydrogen, right? But hydrogen can only have one bond at a time, so we have to break a bond. So if we broke a bond, where did we put electrons? In the antibond. If we broke a bond, we put electrons in the antibond. So here we broke the sigma OH. We put electrons in the sigma star OH. That was our acceptor orbital here. And so we didn't have any of our other good orbital acceptors, right? Like we didn't have an empty 2p orbital, we didn't have a pi star. So we're left with a sigma star. But again, we know this has to have happened because we broke that sigma bond. So with that, I want you to try out these two. And again, first, figure out, are we in nucleophile electrophile land or are we in acid base land? And the criterion is, did just a hydrogen move? And then second, trying to figure out what your acid base nucleophile electrophile are and the donor acceptor orbitals and trying to do the arrows here. So take a couple of minutes. GM? Your GM. Your Rose. Aria Fabian. You start with an M, Micah. So. Lavinia. I had to look. I knew it was L. We're getting there. Nora. Ahmed. Me. Sue. Simran? Wait, Simran or Simran? Simran. Okay. Evie.
We gotta get you a name tag though.
Mine is spelled not the way you would think.
You said it's like Elias, but it's with S. Train me, you mean? Yeah. Asias. Okay. Work. So, I have the spelling too. Like that's the thing. I've also been trying not to use the list. Asias. Asias. Work. Jerry. Alyssa. Yes, or but not on Friday. So section 4 is going to be held Thursday evening.
Wait, what? Sorry.
Section 4 is not being held on Friday next week. It's being held on Thursday evening. So, yes, and it's on the course schedule. I think that it's going to be offered at 4:30 and 6:30, and come to the 4:30 if you have Tuesday lab, and then come to the 6:30 if you have Thursday lab. Yeah. So for this second one, are we in acid base land or nucleophile electrophile land? Good. So which one seems like it wants more electrons, the left or the right? The left. So that's going to be our electrophile. It wants electrons. The right's going to be our nucleophile. What's a good donor orbital on the nucleophile? Lone pair. Trend alert. Lone pairs as donors. Groundbreaking. And then what's a good acceptor orbital on the electrophile? Yeah, and what's that specific orbital? It's a 2p orbital on the carbon. So we're going to draw an arrow that goes from the lone pair in the oxygen to the carbon. And here I just drew it to the carbocation because that tells us where we're going. But actually, I need to model really specific arrows for y'all because arrows do count. Like, so for example, up here, this arrow has to start from that bond and go to that atom. If it starts from the H, that is incorrect. Because arrows are showing the flow of electrons. So you need to show where those electrons started and where they ended up. Okay, and then that gets us to our product. Great. So last one is a little tricky. Are we in acid base land or nucleophile electrophile land? We're in acid base because the only thing that transferred between them was a hydrogen. So we know that this is going to go and grab a hydrogen. So what's the donor orbital? Wow, I already drew it. The lone pair on the oxygen. And hey, we no longer have a third sigma bond here. We broke a bond. So what was the acceptor orbital? Sigma star. Very good. We put electrons in the antibond, the bond broke. Okay. But then we would normally expect it to just go on here, right? And we'd have like carbonyl CH2 minus. But that's not what they gave us here in the answer. So we need to draw more arrows in order to get to this. So we need to do something with the electrons in this CH sigma bond that now is being dissolved, essentially. So where are we going to put those electrons? Well, we're going to turn them into a double bond right here. So this becomes a second donor. The sigma CH is going to put its electrons somewhere, and then did we break another bond? We broke the pi bond, so we're putting it into the pi star CO. And so we have one more consequence arrow because we broke that bond. Yeah.
How are we breaking a pi bond? I understand that we're making a pi bond.
So the pi CO that exists right here no longer exists. And so since we no longer have that bond, we must have broken it somehow. The other way to think about it is like, okay, how did this get a negative charge? Well, the electrons that were in this pi bond just got shifted up on the oxygen. Work? Yeah, Ari?
Sorry, I was just thinking.
No?
Actually, never mind. So, so for the first, the lone pair oxygen to the sigma star CH.
Mm-hmm.
So when we draw the arrow for that, so because like sigma stars and pi stars aren't like shown, right?
Yes,
And
you
so
draw,
it goes straight to the H.
yes.
Okay.
So you draw the atom that is going to be attacked.
Okay.
And remember, in an unequal sharing of electrons, it's a larger lobe on the less than electronegative side. So hydrogen is less electronegative than carbon, so there's a larger,
Oh, okay. It's a larger lobe on the left.
yes. Mm-hmm. Yeah.
I don't
Rose.
understand why the lone pair on oxygen is the donor for the hydrogen. I thought hydrogen couldn't accept anymore because of it's like the one bond.
So it's kind of, yes, like hydrogen can only have one thing happening with it at a time, but it can change. Like essentially because this is going and grabbing the hydrogen, then we have to give up this other bond. We have to give up those electrons. But really, we know that this happened because we see she has another hydrogen in the product. And so that's kind of our tip off. Yeah. I'm going to do one more practice with y'all here. And this is back to that page 29. So y'all did the MO diagram for part molecule A. I'm going to give you the MO diagram for part B. And now we're going to try to predict how molecule A and B react together. So, first of all, let's identify the HOMO and LUMO of each molecule. So what's the HOMO of this? The lone pair on nitrogen. Yeah. So we don't even have to go through our list of good donors and acceptors if we have an MO diagram. We just look at the MO diagram. Okay. And then over here, our HOMO is going to be lone pair on the chlorine. LUMO is up here. So I'm just going to write these out so we have them for easy reference. So lone pair on the N, sigma star NO, lone pair on the Cl, pi star Cl. So now, the next question that we are going to do to try to figure out how these molecules are going to interact with each other and what role in the reaction they're going to take on is let's compare the two HOMOs. Which one's a better donor? A lone pair on nitrogen or a lone pair on chlorine? Nitrogen, because our exception is lone pairs on halogens aren't as good donors. So, lone pair on nitrogen is going to be the better HOMO of the two, and this is kind of our losing HOMO. And then, between a sigma star and a pi star, which is a better acceptor? Pi star. Why? Lower in energy. So this is our winning LUMO, and this is our losing LUMO. So what this means is molecule A is probably going to react as our nucleophile, because it has a good donor and a meh acceptor. So let's say this is our nucleophile, And then molecule B over here is going to be our electrophile because it has a great acceptor and a meh donor. So what we are going to do is we're going to have the lone pair on nitrogen go and attack the pi star CO on the electrophile here. So we just put electrons in an antibond. So what happens? The bond breaks. So when we draw our product, we literally are just not going to change the things that we did not mess with. So we still have all these single bonds, HCl. We created a new bond to nitrogen. That nitrogen still has the H2 and the OH on it. And then this arrow right here became this bond. And then this arrow turned into a lone pair over here, which makes a negative charge. And last thing is nitrogen now has 4 bonds, so it's positively charged. So like this is going to be a page of your exam basically, where you have to do an MO diagram. We give you another molecule. You're not going to have to do a second MO diagram, but we'll want you to identify homolumos and then predict what's going to happen in the arrows, even if we didn't teach you this reaction. And do you see how without molecular orbital theory, it would be really easy to think, well, why doesn't the lone pair on the oxygen just attack, right? Because it's another lone pair. But we know that this is a higher energy donor because it's less electronegative. The oxygen's going to be lower energy, so it's not going to be your highest occupied molecular orbital, right? And I think that's where the challenge of MO theory comes together, is like putting all of these pieces together to figure out how molecules react. It's less so each individual step. But with that, it's time for our second hard pivot of the day to an entirely new topic, which is acidity. Let's see if we have a transition. So, acidity. You learned about it in Gen Chem, and when you did it in Gen Chem, you were often doing it with equilibrium stuff, right? So you were doing like KQ, KA, the whole like products over reactants things, and you were using pH, and pKa really only showed up as like a little math problem for you to do, where you did the negative log of something. pKa is going to be our standard way of referring to acid strength for organic chemistry and biochemistry, and so we want you to get a good feel for it. The general trend is lower pKa is stronger acid. But when we say strong and weak, what do we mean? Well, a strong acid is a reactive acid, so something that really wants to give up a hydrogen. And then a weak conjugate base is a stable base, so something that doesn't really want to react. So strong and weak is a proxy for reactivity when we're talking about acids and bases. And the central idea, the guiding light that I write on my paper for every acid-base problem is strong acids have weak conjugate bases. And the flip of it's true, strong bases have weak conjugate acids. So that when we do like acid-base problems, there's often a lot of mental gymnastics that we have to do to kind of keep everything straight in our heads, because it's really a lot easier for y'all to think in terms of the stability of the conjugate base, and that's going to be our criterion for ranking acid strength. You can also think about acids, like do whatever makes the most sense to you, but I'm going to show you the way that made most sense to me. So let's do our like YouTuber boxing match face-off of all of these different atoms and find the winner. Yes. No, weak is stable. Yeah, weak is stable. Yes. Yeah, weak conjugate base is stable conjugate base, which means that we have a stronger conjugate acid. Yes, exactly. So we're going to start off by drawing the conjugate base, both of these. So NH2, NH. What else do we need to draw on this NH? A lone pair and? Yeah, negative charge. Yeah, remember, lone pairs we can either draw out explicitly or we can omit in our skeletal structure things, but we do need to explicitly draw all charges. So now, which is more stable, NH2 or NH minus? NH2, so this one's more stable. So this is the weaker conjugate base, so this is the stronger acid. So NH3 wins. Summarizing it, the more positive formal charge is the most acidic. Okay. Same thing for this one. We have NH minus, and then we have O minus. Which one's more stable, a negative on O or N? O, because it's more electronegative. So more stable. This is our weaker conjugate base. So this is our stronger acid. So an OH is more acidic than NH2. Then we're comparing an O minus versus an S minus. And if we did based on our electronegativity trend that we saw over here, we would expect it to be O. But actually in this case, the more stable one is S. So what this has to do is you have two competing things going on. When you are in the same row of a periodic table, like CNOF, electronegativity is going to be the big thing to pay attention to. Of if it's more electronegative, it's more acidic. But when you're in the same column of the periodic table, the atomic radius is going to have a bigger effect. So imagine you have a negative charge and you have it spread out on this little kind of like beach ball sphere. That's oxygen. And then you could take the same amount of charge and spread it out on a big sphere, and that's sulfur. Which one's going to be more stable? Spreading out a negative charge over a big volume or a small volume? The big volume. Yeah, small volume, it's going to be very reactive. It's going to want to react more readily. And so we know that S minus is more stable, so this is our weaker conjugate base. So this is our stronger acid. And like pKa-wise, this difference between a pKa of about 17 and a pKa of about 8, so it's pretty substantial. Then we have, okay, O minus here by an alkene, and just an O minus. Well, which one's more stable, left or right? Left, because she has, no one said the buzzword, resonance. So, we have a resonance structure. Resonance is like, hey, I'm your ride or die. I'll take on this negative charge with you. We are spreading it out. We are all sharing this burden. Whereas this, it's all localized in one spot. So this is our weaker conjugate base. This is our stronger acid. Then we have resonances like younger sibling, which is induction. So in both of these, we're going to have a negative charge. But here we have two fluorines. And when we have halogens on a molecule, we say that they are electronegative enough that they are going to tug on the electron density and kind of pull it over a little bit. Like I imagine it's like sharing a blanket with someone, and you can kind of tug on the blanket a little bit. But here, you're tugging on electrons that have a negative charge built up. And so when you tug a little bit on it, you are spreading out the electrons a little bit. And so that makes this more stable because you have this, we call it the inductive effect, where it's pulling a little bit of the electron density away from where it's located. That is going to stabilize that negative charge and spread it out a little bit. So this is our weaker conjugate base, stronger acid. And the last one here is if we have nothing else going on and our only difference really is in hybridization, then we say the more S character wins. So in an sp2 orbital, we would say it's 1 of 3 parts S, right? So it's like 33% S and 67% P. In an sp orbital, what percentage is S? 50. So this one has more S character, so it's going to be more stable. Now why? So the way I like to think about it is when you have an S orbital, it's a sphere, right? You're holding that charge actually closer to the nucleus versus a p orbital is further out. So there is a little bit of a stabilizing negative interaction with the positive nucleus. And when you are at such a small scale of like an S orbital versus an sp or versus an sp2, whatever, that it's going to be so subtle that actually that Coulombic effect is going to have a different NPKa. So we're going to have slightly more stable for this alkyne over here. So more stable. This is our weaker conjugate base. So this is our stronger acid. Now, when we have just one column or like one criterion that we're comparing against, we can use our little Cario rules here, and life is fine and good and dandy. But when you have multiple competing effects, it's hard to know what wins, which is why we are making you memorize these pKa values. Like if I told you that like hydrochloric acid has a pKa of -7, I need you to be like, oh shit, that's more acidic than H3O+. Or if I told you that like this drug needs to be maintained at a pKa of around 4, you need to be like, okay, so the carboxylic acids still need to be in place. Like these numbers need to mean something for you, and until you have like this kind of memorized and internalized, pKa's are just numbers. They don't really mean anything. And it's something that I do think will be valuable for you when you are in biochemistry, all the way up to medical biochemistry. Like you were thinking about pK quite a lot when you talk about blood acidity, when you're talking about like functioning of hemoglobin, when you're talking about whether certain amino acids in an active site are protonated or not. You will need to know this. So, commit them to memory soon. And like the functional groups come in on lecture 3 with the functional groups down. pKa, I would say by like next Friday, because you don't want to be cramming them right before the test. But any questions on the kind of Cario intro acid things? Yeah, how are you?
Can you go to the conjugate base for the last example that we did?
Yeah.
Wait, could you just explain how you got the negative and how you got that?
Oh, I just removed a hydrogen here. So like it still has the other hydrogen down here. Yeah,
Okay.
and then-
I get confused sometimes with the alkane skeletal structure.
Yeah, no, it's all good.
Just one issue.
Yep.
Thank you.
Yeah.
So we should memorize all the functional groups by next lecture.
100%. Because lecture 3, we start doing reactions, and we assume that you know the functional groups. And until you know the functional groups, you're going to be doing this game of like, these are all separate things, when we want you to recognize this as a pattern that's happening with all of these types of functional groups.
So wait, which ones do you memorize?
These.
All these.
The compound functional groups, mm-mm.
And then obviously you know like the alcohol base.
Like this stuff, we're not going to test you on. I just introduced it so that you have more tools and to preview what's coming in lecture later.
And I like the sequence of the acid and the alcohol code, and then you do is memorize that for sure. Or just see that.
Sequence?
Or I don't know the reaction, the single reaction.
No, this was just an example to show you why it's important. Yeah, you'll learn this in lecture 5. Yeah. Cool. I do need to move on, but then I'll come back to you later, or we'll ask at the end. So, there is a relationship that we have between pKa and KEQ, our equilibrium constant. Let's do a really quick Gen Chem review. So if our KEQ is greater than 1, do we favor the products or the reactants? The products. So our arrow would go to the right. And then if it's less than 1, we would favor the reactants. So it goes to the left. And when it's equal to 1, it doesn't really favor either of them. It's about equal. Okay. In an acid-base reaction, remember we have acids on both sides of the equation. So on this one, left or right, which one's our acid? How about this? What's the name of this functional group?
Oh,
So what do you think the acid is? Ding dong, ding dong. So this is our acid, which means this is our base. And we know bases have conjugate acids. So our acid on the other side is the NH4. Okay, well what's the pKa of a carboxylic acid? 5.
I still see with the
Then what's the pKa of NH4?
what are the 9?
It's 9. Yes, we can scroll up. So, yeah, hydrogen cyanide, great. So the way that we get the KEQ is we do 10 to the power of the product acid pKa, 9, minus the reactant acid pKa, 5. So that's going to be 10 to the 4th. So is that going to be product or reactant favored? Product favored because it's greater than 1. So that's a skill that you need to know how to do. I'm going to skip this practice 4, which is a challenge problem just ranking acidity because it's more of what you've seen. And instead, to practice acidity, let's look at this extra challenge problem, which is, remember, the type of questions that we're going to do on Fridays. So if you are a print problem set user, it's in this orange book in the last like 10 or 15 pages is where it has the extra challenge problems printed. So is there anyone that needs this? Yes. There you go. And then also Lavinia. I have that you ordered a print copy as well. Do you want it? Okay, work. Yeah. Sorry? This is the extra challenge problem, but it's in the section notes as well. So, I want to give you guys a few minutes to try this on your own, but I will give you a few comments to set you up. Remember, extra challenge problems are PSET level problems, they are exam level problems. So, it's at the very end. It's in the last like 15 or 20 pages or so. So, this molecule is a common dye used as a pH indicator. At low pH, the molecule is colorless and has the structure depicted in A. Deprotonation of A with hydroxide yields water and monoanion B. So, a couple things. We are going to deprotonate this molecule, and hey, what are our only hydrogens that we could really deprotonate? These, right? So our hydroxide is going to deprotonate them. So we know we're going to have that arrow, right? Okay, and then she's going to be turning into water. And then we're going to have another structure here that they say is a monoanion. So we know it's going to have a negative charge. Okay, now the last part, which is the most crucial, which appears pink and in which there is no longer an sp3 hybridized carbon. So B has no sp3 carbon. And where's our sp3 carbon in A? In the middle. So somehow we need to break one of these bonds. We need to go from the action happening here, somehow carry it down with curved arrows, and break a bond here. Woof. So I'm going to let you try that. And then you can do parts B and C separately, and B and C are easier. So remember, getting all the partial credits. So for part B, they give you the pKa of this thing as 9.5, and they ask you to calculate the KEQ by using the formula that we just did. Then for part C, they give you another molecule that looks very similar and says, okay, what's its pKa relative to the one that's given here? So I'm going to give you like 3 or 4 minutes to try to work through this and try to see what comes of it, and then I'll circulate.
Why did we start with that first arrow?
Because they tell us that hydroxide deprotonates it.
But we could have gone to the other way as well.
Yeah, they're symmetric, so you could have done this way, and in which case you'll do some arrows along this path. Yeah. Simmer. Asias. Work. Neat. Evie.
Oh my gosh, seriously.
Wait, Micah, are you not a tablet user? Are you not a tablet user? Like, you didn't request Prime? Oh, well.
I realized that I left my charger.
Heard. All good. The annotated one will be uploaded tonight, so. Alyssa, I will need you to keep quizzing me because I can't properly guess yours because I see your name tag every time. Also, are you Rosalinda? Oh, word. I was like, you just adopted an alias.
Yeah, we have no joint custody.
Word. Are you sure you don't have 2/3 custody? Because you have two.
Yeah, it's where it's all owned by Alyssa and Alyssa.
Two Alyssas. Drama. Hmm.
Oh no, it's not.
I'm gonna give you like 1 more minute.
Oh, you're putting this here basically, and then you're putting this here. Yes. Oh, okay.
Go to the next one. Now,
So now
you
this
want
is
to
two.
now this is question medicine and then
Well, I
this
forgot all the
one.
arrows and I just went for
This one. This one. To the other one.
And then this one can flip back here.
So, we have just grabbed this hydrogen and donor accepting orbitals and everything. We have a lone pair in the oxygen. And what's our acceptor orbital? It needs to be an empty orbital, right? Sigma star OH. So if we put electrons in an antibond, the bond breaks. And we have to figure out what to do with these electrons. Normally we'd think that they would just go to the oxygen, but we need to carry that forward. So where should we put these electrons instead? To make a double bond here. So, okay, but then that creates an issue of this already has 4 bonds, so which bond can we break easily? The double bond. Let's jump it down again. And then now this carbon has 4 bonds because there's a hydrogen there. So we need to jump it forward 1 more time. And then, okay, moment of truth. There are 4 bonds. They're all sigma bonds. We need to break a bond. Which bond do we break? Why? Why? So, if we broke a sigma CO, then we put electrons into what orbital? If we broke a sigma bond, we put electrons in an antibond. So our choices are we could have put electrons in a sigma star CO, or the other ones are sigma star CCs. Which one's a lower energy one? Well, the CO. So this is the better acceptor. It's all MO theory. It's all MO theory. I'll come back to it, I promise. So here, I'm going to draw the structure. So like this arrow became a double bond. This arrow moved a double bond here. This double bond on the end was left alone. And then we have another double bond that was created here. And then we kicked off O, and it now has a negative charge because it initially had 2 lone pairs, and then this third arrow made another lone pair on it. So it's monoanion, it has a negative charge, and can we confirm there's no sp3 hybridized carbon in it? Work. That's it. So it's tricky. Like, y'all have never seen arrow pushing like this before, but really a lot of these arrows are related to resonance. And this is an acid-base arrow that you've seen before. And so, like, right now, if I were to give you a test over what you've learned so far, this would be an unfair test question because it's beyond what you have seen now. But in 2 weeks from yesterday, so in 13 days when you take the first exam, it will be a fair question because you have seen this in the practice and you'll see it on the problem set. Now, KEQ, we said the pK of this is 9.5 by the problem. What's the pK of water? 16. So this is going to be 10 to the 16 minus 9.5, so that's 10 to the 6.5. So is it product or reactant favored? Product favored, pretty significantly. Then compare this molecule to this new tetrabromo. So we've added 4 bromos. So what effect does this molecule feel more? If we've added halogens on it, it has more induction and more inductive effect. And more induction makes something more, it makes a conjugate base more stable. What is it due to acidity? Yeah, it makes it more acidic. Sorry, there are many ways that that prompt could have gone. So here we have more induction effect, so we know this molecule is going to be more acidic. The other way we can think about it is if we had a negative charge, then putting bromines here is going to help spread out that negative charge by tugging on the electron cloud. So this is more acidic, it's the lower pKa. So that's all we do for this for now. The last part that we're not going to get to is it's giving a bunch of different bases and says which base would deprotonate this but not this, which is kind of a tricky conceptual question to think about. So I'd encourage you to think about it because I think that this could be a good example of a test question. But all that being said, thank you for coming to section. I appreciate it. Have a good weekend. I hope to see you at Help Room on Monday. Email me with questions. I'm going to stick around and answer some questions, but that's it. Thank you. Wow.